In this video, I'm going to go into a little bit more detail about our position operator, x, and our k operator, which is the derivative operator, the Hermitian derivative operator, I keep calling it. So to kind of review, in position space, then x operating on a vector space that is position dependent leads to x times that vector space back again. So x is the eigenvalue. If I now operate with the k operator, then what I'm doing is basically a minus I, the derivative of the function with respect to space x. So it's a new transform space, which is basically derivative of the function space back again. Now, the interesting thing is we can take a look at combinations. So if we have the combination of the operators of k first, followed by an operation of the position operator, operating on our function space, we're still working in position space x. Then first I would operate with k. So I would get x something like that, which is now a this ket right here is just a function. It's a function of position x. So the position operator operating on it just puts an x in front. So in the end, I get something that's basically minus I, the position x, times the derivative of the function with respect to x. If we work through, change of basis and normalization, we would get basically something that looks like that. Now let's look at the operation in reverse order. So let's operate first with the position operator x, followed by the k operator. So here's where things get interesting, because first operating with the position operator x gives us an eigenvalue of x. So I have k times x times the function space right there. And now the k operator is the derivative. So that would mean I would have minus I d dx of x times the function space. And so now we have to apply the chain rule. So first we have to operate on x, and then the second we have to operate on the function space. So what I would get is minus I, the function space back again, minus ix, the derivative of the function, like this. So there's two terms in it. And so this is why the order of operation is really critical, because we can't take k first and then followed by x, because you notice that you get two different things. And so what this is leading to is the fact that the product of x and k, it does not give you the same result if you operate with x first and then k. So basically what we're saying is that the combination, the operation of these two together is non-commutative. They don't commute. So that means we can actually take the commutator and operate on our function space, like so, which is the same thing as saying xk minus kx operating on that function space. So the functions are distributive, so we would get basically this minus kx operating on the function space, like that. And so now if we plug in our previous results, then what we would get is minus ix, the derivative of the function with respect to x, minus ix, the derivative of the function, minus I times the function. And so if we work through the math, then these first two terms cancel each other, and we're left with I times the function again. Or written more formally, the commutator of position and k operating on this function space f, this ket, is equal to the complex number I times the identity times that function space back again. Or if we take off the function space, we have that the commutator of these two operators, k and x, is equal to I times the identity. And so this is really interesting. So we can actually work out here that the commutator of these two particular operators, position and k, is going to give us the imaginary number I times the identity. And what's even more interesting is we finally get a physical explanation of what k is going to become. So in the next couple chapters, we're going to find that k is really related to the momentum by Planck's constant h bar times that operator, where h bar is h divided by 2 pi. So basically what it turns out to be is if we're talking about wave functions, which are these quantum waves, the k operator is related to the wave number, or the the wave number, which is 2 pi divided by the wavelength of that quantum wave, and we can get the momentum from de Broglie's relationship, where the linear momentum of this quantum wave is Planck's constant h bar times that wave number. But now we're writing it in operator form. And so what we have is a momentum operator. So P is the momentum operator, and the commutator of position and momentum is just the position and h bar k, which is h bar times the position operator and the k operator, which is I times the identity. So we get I h bar times the identity. So the commutator of position and momentum gives us I h bar, which is key. And this will come up later on. But the interesting thing is that position and momentum are related. I mean, they're what we're going to find out we're going to call conjugate coordinates. And so this relationship turns out to be true for other conjugate coordinates. So the one that comes up, and we'll see later on, so I'll give you a little bit of a spoiler of another conjugate coordinate, is time, and energy. And so we could eventually we could come up with a time operator and an energy operator, and those two operators are going to have a commutator, which is going to give us the exact same relationship of I h bar times the identity. Now, before I close the video, what I wanted to do is always to give you a word of caution, is that when we talk about these commutators, we always write it down in this way, and we always seem to leave off the wave function or the vector space. And so just remember that when you're working through a commutator like the position and the momentum, that what you're really doing, or you really should do, is to operate on some function space, because things like the momentum operator is a derivative. And so you need to, when you work out the commutator, you need to work out this derivative. The derivative has to operate on something. And so, and it has to be, and the order of operation, of course, matters, because, as we found, that when we operate on the momentum, after the position, that position operator gives us a value of x, and we have to take the derivative of that x, use the chain rule, so forth and so on. So just remember, a word of caution is that when anytime dealing with the commutator, always remember to evaluate it with a vector space in mind, something it can operate on, and then do the algebra to clean it up.